So here we have an example of an axially loaded member where we're trying to calculate the change in length of the member, but the cross-sectional area is non-constant. It's a non-prismatic axial member. And so now with our general form axial deformation equation, we can deal with an axial member like this. And so here, just to explain the problem, we have a column, it's fixed at the left at point B, it's free at point A, it's subject to a point load P that's applied at point A, and it tapers from a large diameter, it's a circular cross-section, a large diameter at B to a smaller diameter at A over the entire length. The radius of that cross-sectional area as it varies is given to us as a function of the distance from point A. So at a distance x from point A, we're given that the radius is a function of x, and that function is given to us up above. It's given as the radius is equal to r naught, some value r naught, a constant value, times e to the ax power, where r naught and a are just given coefficients, they're not unknown values, and we can assume that they're known for the problem. So in order to solve for this change in length, the overall change in length of this column, we need to use our general elastic deformation equation that we derived previously. And that is simply the change in length of an axial member is equal to the integral over the entire length of the member of n of x. The internal normal force is a function of x dx over the cross-sectional area A as a function of x times the modulus of elasticity. And again, this is our general format equation. We can manipulate it, simplify it if we need to. And in this case, we can make some simplifications. Let's just go through kind of the steps that we would take the analysis, and we'll take some of these values out of the integral as we go through. The first one is relatively easy. Just looking at this equation right here, like I mentioned before, we're not going to have any examples where the modulus of elasticity varies along the length of the element. We're always going to assume a homogeneous material, and so the E can come out and go in front of the integral because it's a constant value. So here we need to find now a function for the internal normal force and a function for the area, and we're going to find that one of those is also a constant. So the way that we would solve for the internal normal force is always the way that we solve for the internal normal force, which is by making a section cut and then by using statics to solve for it. So in this case, we'll make a section cut at this same arbitrary distance x. And so I'll make a section cut at that arbitrary point x. I'll make a free body diagram out of it. I'll draw it in 2 dimensions just to make it a bit more simplified. And here's going to be our free body diagram with the section cut at x. So here's my section cut. Here's the 2-dimensional representation of the tapered column out to the free end at A. And what we're really concerned about here is the internal normal force, and I can draw the internal normal force before I even draw on any external forces because we always draw it based off our sign convention, which tells us that we assume everything is in tension and that's a positive value. It might turn out to be negative. All that tells us is that it's actually in compression. But when we draw our internal normal force, we draw it in tension. In this case, that means we point it away from the section cut. So in this case, away from the section cut would be pointed to the left. Again, if I kept everything to the left of the section cut, it would have been pointed to the right away from the section cut. So that's my assumed direction of n. Now I have to also draw on my external loads. And the only external load that is shown here to the right of the section cut is the point load at point A. I have a couple other things to make this free body diagram more complete. This distance right here is x. Technically, we need to have a coordinate system on here as well too. I'll draw my coordinate system. Again, this is arbitrary, any direction. It won't affect my final result. The only thing that would affect the final result would be the assumed direction of n. So all that I have to do now to solve for n is I want to sum the forces horizontally. So I will sum the forces in the x direction equal to 0. My coordinate system says that forces pointed to the right are plus, forces pointed to the left are minus. Again, that won't affect my final answer. It's just how we add things up relative to each other. So that tells me going from the far left to the far right, n is pointed to the left, so that's minus n. P is pointed to the right, so that's plus p. And because this is equilibrium, everything adds up to 0. And if I rearrange that, I get the very simple result that n is equal to p. So in this case, n is a constant value. X is not part of the equation here. We don't have any distributed external loads, so x is not part of equilibrium. So in that case here, n is a constant value. And just like we did with the modulus of elasticity, we can take any constant value out from inside the integral. So that makes our life a little bit easier. We've taken normal force out, we've taken the modulus of elasticity out, and now we have to solve for the last piece of our puzzle, which is simply the area. And so here, taking a look at the geometry, every cross-section cut that we make is going to result in a circular cross-section. And my circular cross-section, so here we're trying to calculate the area. My circular cross-section is given to us with a radius. That radius is equal to r naught times e to the ax. And all that we need to do is plug this. This is actually a function of x. I'll make that as clear as possible. The radius is a function of x. It changes whether we're at point A or point B or anywhere in between. And so the area of a circle is also going to be a function of x. It's going to be equal to pi times r squared. I just substitute my function for r of x into my equation of a circle, and I get pi times r naught e to the ax squared. And this is relatively easy to square that because I can just multiply the exponent by the 2. I can multiply the exponent of r by 2 as well because r naught to the 1 is all that this represents. And so we get pi r naught squared e to the 2ax. So this equation here, this is my function for the area as a function of x. And it's important to point out that this portion right here is constant. It does not depend on x, whereas the e to the 2ax portion, that's dependent on x, and so that's a function of x, and that needs to stay inside the integral. So if we were to simplify this down a little bit, I get n divided by e times the integral from 0 to L of dx over a of x. This is a of x right there. Pi times r naught squared times e to the 2ax power. But just like we said down below, pi times r naught squared is a constant, and so that can also come out. It is, I mean, you could still integrate it. It wouldn't make any difference whatsoever, but we can pull that out as well. So just to make the integration as simple as possible, I will rewrite this as n divided by pi r naught squared e times the integral, excuse me, from 0 to L of dx over e to the 2ax power. And if you wanted to try to simplify it even more, again, it's still a relatively straightforward integration, especially with a table. You could rewrite this if you wanted to as n over pi r naught squared e times the integral over the entire length of e to the minus 2ax dx. Either of these forms are relatively straightforward, especially with the integration table. So on the exam, I've mentioned that you get what's allowed on the NCEES tests, the best calculator being a TI-36X Pro. So a TI-36X Pro will not do anti-derivation for you. It can do definite integration, but not indefinite integration or anti-derivation. So the power rule, you're responsible to just know that should be pretty straightforward. Here, e to the power, integrating that. I would give you an integration table on the exam. It's not a calculus class, but you should be pretty comfortable with it. But you're responsible for putting down some basic integration equations that you're responsible for, trigonometric functions, sine, cosine, tangent, things like that. And this is kind of a stretch to not need to know, but I would give you a table that you could use integration table for a problem like this. What we end up getting, we have to do a little bit of simplification, but we will get at the end that the total change in length of this member is equal to n over pi r naught squared e times the result of this integral right here. So we integrate this, we evaluate it at L, we evaluate it at 0, and that's an important step here because we get a -1 as a result. And if I do a little bit of simplification with the result, it's not too bad. I get n, well actually, that's a good point here. We know that n is equal to p, so I can substitute that in here, and that will make it more relevant to the specific problem. So it's equal to p divided by 2a pi r naught squared e times the quantity 1 minus e to the minus 2al. And so this value here is going to end up being positive for a positive value of p, which makes sense. Sometimes people see the minus symbol here and they say, well, you're going to end up with some negative value, but clearly if I have a positive p, I should be getting a positive deflection because it shows tension. Just realize here that this quantity is going to be greater than 1. 1 minus, because here we have a -2 in the exponent, this is going to end up being less than 1. And so we would get a positive value here, positive value here. We would get elongation, and so everything works out okay. Again, in terms of integration, this is about as complex as you're going to see on the exam. But you definitely need to brush up if you're not familiar with power rule, and you're responsible for basic trigonometric functions to put on your note sheet, sine, cosine, tangent, things like that. For natural logs and exponents, I would give you a small table of integrals if you need it. So here's our final answer, and you should also consider working most of your problems in variable format. It's free game on the homework or on the exams to ask you to solve something leaving everything in variable format, and even if it's not required, it's a really good practice to solve everything with variables, and then at the very end here, this is where we would plug in discrete values for A, R naught, E, length, things like that, P as well. You'll end up finding errors more quickly this way, and you can make sure the units work out more easily this way as well too. If at every step you're plugging in large numbers and trying to keep track of units, you're going to end up having more trouble than it's worth. And so I would strongly recommend, even if discrete values are given, not plugging them in until the very end of the problem.